Hi there everyone, I'm just going to go through the example 3 from the sheet I gave in the last session about absolute maximum, absolute minimum. There are just a few things to note about application questions of this type. For example, you got to get used to the terms like maximum volume. What are you really trying to find there? What are they really asking? Show that the volume is maximum for this value. What does that actually mean? The hard part here is to actually relate the mathematics with a real-life application. And in this case, we're talking about x length. Okay, so x meters in terms of the sides of the height and the volume of this shape. So volume. So obviously, one of the few key things or restrictions you have is volume cannot be greater than 0. That's the first thing you've got to be able to keep in your mind. Volume has to be greater than or 0. Actually, it can't equal to 0 as well. Same thing with your x length, cannot be equal to 0 as well. So let's start off drawing our problem, because it's always about visualizing what's actually happening, and then that's when it makes it easier for us to solve. So I'm just going to try to move this down. We're going to make this easier for ourselves, and we're going to draw right here. We're going to say, okay, well, here's the thing. You've got a square metal of side length 2. That's what the problem was saying before. So it says right here, from a square piece of metal, a side length 2 meters. Okay, so side length 2 meters. 4 squares are removed as shown in the figure shown. So as you can see in this left-hand figure, the squares have been removed. Obviously, what's happened is I've got a square that has a 2 meter length from here to here, okay, and a 2 meter length from here to here. So from here to here. Alright, so you got 2 meters by 2 meters, and they're saying they're going to cut out an x meter square from each corner. Now we don't know. We just know this is x meters and this is x meters. So it's from here to here is x. From here to here is x. That's all we know. We're just going to cut off this section here. X, x. Cut that off. And right here it's x, 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 and x. So as you can see, that means when I actually start cutting it out, this is what's going to happen. I'm going to have the shape, which coincidentally actually looks like the shape on the left-hand side. So that's the problem. That's all they've done so far. They've just pretty much cut out that x part out. So I've just cut out the part, and this is my shape. Okay, so I'm just saying this is x, which most of the time, you got to realize, okay, I'm going to actually fold this shape into a 3D shape. That's what they're saying. They're saying they're going to fold this. The metal is then folded along the dotted lines to give an open box with sides of height x meters. What does that mean? Well, if this is my shape and I was to fold it, this is what my shape looks like. You can sort of picture it. So it kind of looks like this. Okay, so I'm just folding everything up. Obviously, this is my x meter length. X. And that's just the height. And obviously this is what I don't know. Okay, right now I don't know how long this is, and I don't know how long this is. What does that correspond to in terms of our diagram? This is the length that I'm actually talking about right now. This is the length, whereas x is what you're folding up. So try to visualize that in 3D. Now the problem is, the question is, how long is this part here? Well, think about it logically. If you know that from here to here is 2 meters, and you also know that you're removing part of this length here, which is x, and you're also removing this part of this length, which is x again, then obviously the desired area that you want has to be whatever the total length is minus the 2x's, which I know is 2 meters minus the x, which we can rewrite as 2 minus 2x. So this tells me this is 2 minus 2x. Which conveniently as well, because this is a square, the length is also 2 meters, so I know this side has to be 2 minus 2x as well. Okay, so I've got my problem. This is my problem here. Okay, now I'm just gonna bring this all the way to our actual question, just so you can relate. Obviously, when I'm doing the problems, I only draw this shape right here. I don't draw the rest. You have to get used to the mindset of what you're really trying to do. So let's have a look at the question here. It says A, show that the volume V meter cube is given by blah. Okay? You don't have to look at that equation and go, oh man, that's so hard. The question was already in the first 4 words. Show that the volume. Okay? Show that the volume is given blah. You just want to find out the volume. That's all it's asking. If I asked you to find a volume of the shape, okay, you would just say, well, volume of the shape, which is a square base, or cube, really. Actually, it's more like a, what would you call it? Probably a rectangular prism. Then you'd say that's actually just, okay, so the volume is, again, A times H. That's your general rule back in year 8 when you're learning volumes. And area is the area of the cross section, which in this case we can say is the area of the top, which is A multiplied to the height, which gives you the volume. Yeah, it's 3D shape. This is area. Right here is area times height will cover your volume. That gives you the capacity. So to find out the area, it's just length times width, because it's a square, times the height, which in our case we know is x. Okay? So solving for this now, let's do it. Length we know is 2 minus 2x. Width we also know is 2 minus 2x. And times h, well, h we know is x. Now we combine this. This is actually the same term, so I can actually write it like this. 2 minus 2x, or squared x. Now, if the question says simplify, this would have been correct, but obviously I'm trying to prove what? I'm trying to prove that my volume equals to this, and clearly this is an expanded form, so what I have to do is I have to expand this. Now, if I expand it, again, going back to quadratics, how well you're good with quadratics, square the first term, which is 2 squared, which is 2 squared, 2 times the terms inside, so 2 times 2 times negative 2x gives you negative 8x, and then plus 4x squared, and this is all being multiplied to x, which if you expand this brackets again, that now gives you 4x cubed minus 8x squared, and the 2 squared is 4, so that's plus 4x, which is proven. Okay, so 4x cubed minus 8x squared plus 4x. There we go. I've proven that the volume is equal to blah. Okay, and this is the way to show. You have to start off with an approach, and then a method, and then a justification. Don't ever do show in the sense where you sub a value in, let's say sub x equals 1 in, and then say, there you go. Okay, it then proves that the volume for blah is true. Okay, it's not asking whether it's true or not. It's asking you to show why the answer is as it is. So this is actually how you would do it. Okay. Next question. Let's go to B. B is probably the hardest one to do here, because a lot of the time students don't understand what the maximum volume is. What are they asking? Okay. So it's saying find the values of x such that gives the box its maximum volume and show that this volume is the maximum for this value. Let's start off with the first part. Let's just find the maximum volume. What is the maximum volume? Part B. What is maximum volume? Sorry, I'm having a bit of troubles with my pen. So how to find max volume. Well, think about it. If I did give you a graph, are you serious? Alright, if I asked you to draw a graph, this is what we're going to have. Okay, so from here, if I asked you to draw V, so this is X, and this is V. Hypothetically, whatever the graph looks like, I'm just asking, well, what if the graph reaches a maximum, because it's a volume equation, right? But actually, just to be more realistic, we know our equation before, if we were looking at it, this is a cubic function. Right here is a cubic function. So I know v in terms of x is going to be a cubic type shape. So it could be like this. I don't know what it is. But let's say it does look like this. Okay? If it does look like that, when you're asking for the maximum volume, obviously you're trying to find when is volume the greatest. Well, obviously it's at this point. But conveniently, in a cubic function, the maximum volume right here is actually a stationary point. So in this stationary point, we know that because it's a stationary point, we can solve this. Stationary point, which we know we can find this by finding the derivative dv dx, okay, is equal to the stationary point, which at that stationary point we know dv dx has to equal 0. Why? Because at that point the gradient, it's 0 because the maximum at this point, remember, it's the gradient of your tangent. Now if I draw it with another color, what you can see, this is my tangent line. My tangent line has a gradient of 0. And the gradient of 0 means that the derivative, because this is your gradient. I'm just saying at that point the gradient is 0. Remember I said everything you're doing is about the gradient of your tangent line. So the gradient is 0. Now all you have to do is find out dv dx when it's equal to 0. So going back, we know that the equation v, okay, is equal to 4x cubed, what was it again actually? It was minus 8x squared plus 4x. Okay, minus 8x squared plus 4x. So the first things first is I need to find out dv dx. Okay, so finding out the derivative, let's find out dv dx, which is equal to 12x squared minus 16x plus 4. Did I make a mistake? I hope I didn't. It's cubic, bring the 3 down, 12, yes, okay, it's good. Now, I found the derivative, and remember I know that the max volume occurs when dv dx equals to 0, when the derivative equals to 0, or when the gradient equals to 0. Okay? Gradient of your tangent is equal to 0. So having said that, I can now find, alright, well that means 0 is going to equal to my derivative, which is 12x squared minus 16x plus 4, which conveniently I can see that they're all, there's a common factor of 4 for each one of them, so I'm just going to take out 4 as a common factor. That becomes 3x squared minus 4x plus 1. And what I can do now is I divide both sides by 4, which conveniently just makes the problem slightly easier. 3x squared minus 4x plus 1. And you can factorize this to solve for x. So if I factorize this, this now gives me, let's see, 3x bracket x 1, 1, so negative 3, negative 1. There we go. So factorizing it now, and I can use null factor law to solve for x, and that tells me that x, okay, x has to equal to 1/3 here, and x over here will equal to 1, using null factor law. Okay? Up to here, this is probably, in general, let's say, talking about year 12 mathematics, you're probably getting 1 mark for stating this line here, and then the second mark for getting this point. X equals 1/3 and x equals 1. Everything beforehand, you don't get a mark for. Okay? It's just to illustrate the problem for you so that you can see what you were meant to do. Okay, now that you found out x equals 1/3 and x equals to 1, what does that tell me? That just tells me that I now know the maximum could be at 1/3 or it could be at 1. Because remember the graph I drew up here, I was asking when it's the stationary point has a derivative equal to 0. But that's the thing. you don't know where the derivative equals to 0. You only know, you do know where the derivative equals to 0. What you don't know is which one is the maximum. Okay, now logically, I can figure this out because it's a cubic function, but generally you wouldn't be able to. So you just found out that obviously you have a point, you've got 2 points of stationary points, one here and one here. What you don't know is whether those points are maximums or minimums. Now, because I've drawn a cubic graph, you would say this is the max and this is the min. However, if I didn't draw that diagram for you and you just found the derivative, then this is what you would have had. You would have just found out that at 1/3 and at x equals to 1, we've got a stationary point. Now, the question is that stationary point a maximum, or is it a minimum, or is it a point of inflection at these points? I don't know. See, at 1/3, I don't know whether the tangents are, the tangent's 0, but what I don't know is what type. Same thing at 1, I don't know whether it's a minimum, maximum, or even a stationary point of inflection. I don't know. At this point, I have no idea. So your job next, which is in the next part of the question, if you remember, it says here, show that the volume is a maximum for this value. Okay? So you're trying to find the maximum. Now, if you remember, I said that once you get to this step in Year 12, you need to take the next step to get the last mark, which is proof. It's a 3-mark question. The show question is a 3-mark question. You have to show proof. How do you show that 1/3 or 1 is the maximum? Well, that's where you're going to use a sign diagram, which is over here. A sign diagram. What is a sign diagram? Well, you're going to label like this, okay? You're going to write out x. You're going to write out dv dx, which is the gradient. You're going to write out the shape or visual, what shape of the tangent looks like, okay? Now, let's think about this. I'm just going to draw some columns, just so you can visualize here. I know that so far at 1/3, the gradient is equal to 0. And I know that the shape of a gradient that's 0 looks like this. It's a horizontal line. That's my tangent. Yeah? Same thing with at 1. I know the gradient's 0, because dv dx is equal to 0. Yeah? And again, the shape is 0. What I don't know, okay, what I don't know is any number before 1/3 or any number between 1/3 and 1, whether the gradient is going to be positive or negative. Meaning, I don't know if it's this shape or any shape. Okay, or it could be another 0, but it wouldn't be because we solved for 0 already. Okay, so what we're trying to test now, okay, is we're trying to test if it's a maximum point at 1/3. That means the gradient to the left needs to be positive. Okay, it needs to be a positive gradient, and the gradient to the left, to the right, needs to be negative. Which this is, as you can see, that gives you a shape that's maximum. Gradient positive, gradient 0, gradient negative. Okay, so that will give you an idea that it is a maximum point, and that's how you actually prove it. Okay, so what you have to do now, and this is all trial and error, you pick a number less than 1/3 so that you can find out dv dx. Now remember, dv dx, which we found the derivative, was 12x squared. What was it again? It was 12x squared minus 16x plus 4. So minus 16x plus 4. And we want to pick a number less than 1/3. Now I'll probably say 0. 0 is the easiest one because if I sub 0 in, so at x equals to 0, dv dx equals to 12 times 0 squared minus 16 times 0 plus 4. So that tells me this is positive 4. I don't really care what 4 is or what the gradient is. I just need to know is it positive or negative. And I know it's positive. Okay. Same thing with the next one. Between 1/3 and 1, between these two, I want to pick a number that's between 1/3 and 1. And in my case, I'll probably choose, I'll go with half, because half just, it's always easier to work with number 2's, okay? So half. So let's think about it. At x equals to half, what would dvdx equal to? Well, it would just be 12 times half squared minus 16 times half plus 4. Okay, so plus 4. So let's solve this. This is just 12 times a quarter minus 16 times a half, which is 8, plus 4. And a quarter of 12, which is 3, minus 8 plus 4. And that gives you negative 1. So I know that the gradient dvdx is equal to negative 1. What does the shape look like? Well, then that means this is a negative gradient. And right here, I'm already showing that at 1/3, x equals 1/3, it is a maximum. That's a local maximum right there. Okay? And so then the next point I need to find is pick a number after 1, and I want to know what my gradient is, because currently this is what I have. I've got gradient negative, gradient 0. I don't know what the next one is. So let's sub in, let's say 2. Okay, at 2, again, at x equals to 2, dvdx, what is it equal to? 12 times 2 squared minus 16 times 2 plus 4, which, that's what, 48 minus 32 plus 4. And we can already tell 48 minus 32 is going to give you 16 plus 4, so that's 20. So you know that it's going to be a positive gradient, okay? So positive gradient. There you go. So that actually proves now, therefore, at x equals 1/3, you can say that, well, because the gradient, actually it doesn't look like that, it looks like this, because the gradient looks like this, 0, positive, and then negative, you can say it is a local max. Whereas at x equals to 1, we can show that it was negative, then 0, and then positive. This is a local minimum. Okay? You don't have to put that extra part there because x equals 1/3 was what you were looking for. So going back to the question, I've now answered part B. And then lastly, it says sketch the graph of v against x for a suitable domain. Well, this comes back to, sketching the equation on your calculator, or if you knew already, the gradient or the graph was v equals to 4x cubed minus 8x squared plus, what was it again, 4x, okay? That's your graph, and obviously I can actually factorize this to, like take out x as a common factor, and that gives me, and take out 4 as well, so 4, that gives me x squared minus 2x plus 1, which I can actually factorize this further. Come on, okay. I can factorize this further, becoming 4x bracket x 1 and negative 1. Okay, so actually I know this graph this is a cubic function. This goes back to what you learned in term 1 about cubic functions. So this is 4x bracket x minus 1 squared, which I know just based off my understanding about cubics, there's a x-intercept at 1 and x-intercept at 0 using null factor law. Okay, it's when v equals 0, x equals to 0, or 1. Okay, so how does that help me sketch the graph? I can say, alright, this is v, this is x, okay, and I know the graph has an x-intercept at 0, and I know it has an x-intercept at 1, okay, but it's a turning point. Remember, there's that little square right here, okay, that tells me there's a turning point there. And not only that, I found my maximums to be at 1/3, this is where 1 is, and at 1. So at the maximum, I've got a maximum of this point, and the graph goes up, and it comes back down, and it's meant to continue. Okay? What we need to understand here, when you're sketching the graph, that doesn't look wrong so far. There's nothing wrong so far with the graph. Okay? But there is. You see, the problem with the box, if you think about the box, you can't have an x length of 1, because if it's 1, volume equals 0. But how can you have a box that has 0 capacity? That doesn't make sense. So technically, at this point and at 0, you can't include it because it doesn't exist. Okay, so those points don't exist. So what does your graph actually finally look like? Well, if this is v and this is x, then the graph is actually not including 0. It goes up to a maximum, and it comes back down at 1, which again it doesn't include, and it stops there because that's the last point that it could actually be, and then the rest is just not included. So I know now x equals 1/3. This is where 1 is, and that's 0. And that's my graph. Right there, that's my graph. Okay? So that's answering the question, but obviously what you got to do as well is find out that maximum point here. When x is 1/3, what is my y value? And just using my calculator, I found out that the y value is equal to 1/3. I mean, not 1/3, 16 on 27. Okay? You can type that in your calculator solid or do it by hand if you wanted to. But you know, either way. But this is your graph. Part C, that's how you answer the question. Okay? And sorry it took 26 minutes. Again, I'm having a lot of issues with this stylus pen. And so as I'm writing, I lose track of what I'm saying, trying to fix the screen. But anyways, there you go. So I'm going to zoom out just so you can see what we've done overall. And this is what you are expected to do for an application type question, which makes sense for your Psycho 2. True? This is how complicated it should be. All right? Thank you.